We often hear names like Marie Curie and know they're important, but do we truly grasp the sheer scale of her contributions? I mean, the seismic shifts they triggered in our understanding of the universe.
It's a great point, and that's exactly what we're diving into today.
Yeah, this deep dive is all about Marie Curie. Her, incredible scientific breakthroughs, the formidable challenges she overcame, her groundbreaking methods.
And the profound, multifaceted impact her work still has on science, medicine, society. It's huge.
We've gathered quite a stack of material for you. We're pulling insights from detailed biographical notes, accounts from the American Institute of Physics, even excerpts from her Nobel lectures.
And some contemporary analyses too, right? Looking at radium's impact today from places like PubMed Central. So we'll cover her early life, the big discoveries, the obstacles.
And those enduring ripple effects. Okay, let's unpack this.
So Marie Curie was born Maria Sklodowska back in 1867 in Warsaw. Her parents were secondary school teachers.
Right, so education was valued in the family.
Definitely. She got her first taste of science from her father and showed a brilliant aptitude for study, like right from the start.
But here's the kicker. Advanced study wasn't really possible for women in Poland then. The University of Warsaw actually rejected her.
Just because she was a woman. Imagine that.
It's incredible. A mind like hers told no. So this wasn't just, a minor setback. It forced her hand.
It really did. Driven by this real thirst for knowledge, she made a huge move. Paris. She was 24, it was 1891, and she went to study at La Sorbonne.
And the challenges must have been immense.
Oh, unbelievable. She hadn't formally studied for 6 years. She struggled with French, especially spoken quickly, serious money problems.
Lived in a cold attic, apparently, piling clothes on to sleep.
Exactly, just trying to stay warm in the Cordillera. But despite all that, she didn't just scrape by. She absolutely thrived. Got Licenciateships, basically degrees, in physics and mathematical sciences.
Wow. And she was one of just, 23 women enrolled there at the time?
That's right, a tiny fraction. Her determination was just something else.
And that determination really set the stage. Then, 1894, another pivotal moment, she meets Pierre Curie.
Yes. He was already an internationally known physicist, though maybe a bit of an outsider in the French scientific scene.
He'd already done significant work, right, with his brother Jacques.
Yeah, they discovered piezoelectricity back in the 1880s. And Pierre got his Ph.D. in 1895 with Curie's law on magnetism. They married in 95.
And crucially, she was allowed to work in his physics lab. That connection, that partnership, it changed everything.
It really did. So fast forward a tiny bit to 1896. Henri Becquerel discovers spontaneous radiation coming from uranium.
That was a spark, wasn't it?
It was. Marie decided to investigate this phenomenon systematically. She started making extremely precise measurements of its intensity.
And she used this special tool, the electrometer.
Exactly, which conveniently Pierre and his brother had invented. Based on that piezoelectric effect, you mentioned how certain crystals generate charge under pressure.
Okay, so how did that help with radiation?
Well, the radiation ionized the air, creating a tiny electric current. The electrometer was sensitive enough to measure that current. Incredibly sensitive, actually.
How sensitive are we talking?
She could calculate activity down to 1,000th of a milligram, even detect amounts as small as like 1/10,000,000,000th of a gram of radium later on. She called it the chemistry of the imponderable.
Chemistry of the imponderable. I like that. Dealing with stuff almost too small to weigh, but with huge effects.
Precisely. And her early findings were, well, startling.
More than just uranium, right?
Right. Thorium emitted similar rays. But the key thing was the strength of the radiation from both uranium and thorium compounds depended only on the amount of the element, not its chemical form, not heat, nothing external.
That doesn't sound right, based on the chemistry of the time.
Exactly. Flew in the face of everything. It led her to this absolutely profound hypothesis. The ability to radiate wasn't about chemical bonds. It was linked to the interior of the atom itself.
Whoa. So the atom isn't indivisible after all.
That was the implication. A truly revolutionary idea. It challenged the fundamental view of matter.
And that meticulous experimental work, that precision, led her straight to this huge theoretical leap. Amazing.
It really was. And a natural led her to the next big question.
Which was?
If radiation comes from the atom, maybe there are other atoms, other elements, that are even more radioactive.
Ah, so she started looking beyond pure uranium and thorium compounds.
Exactly. Her brilliant next step was examining natural ores. She got samples of pitchblende and chalcolite.
And found something unexpected?
She found they were way more radioactive than their uranium and thorium content could explain. significantly more,
So the only explanation.
was that there must be tiny amounts of unknown, highly radioactive elements hiding in those ores.
And Pierre got involved at this point.
Yes, he was completely intrigued by her findings, put his own work on crystals aside, and joined her. They became a team.
How did they even start looking for these tiny unknown things in a complex ore?
They used basically standard chemical separation techniques, break the pitch blend down into different chemical fractions.
And then tested each fraction.
With the electrometer, yes. They followed the radioactivity. Whichever fraction was strongly radioactive, they knew the unknown element was in there, then they'd separate that fraction further, and so on. Painstaking work.
Methodical, and it worked.
It did. July 1898, they announced discovery number 1. A new element, chemically similar to bismuth. They named it polonium.
Polonium.
After Poland.
Exactly. A tribute to her homeland. Then just a few months later, December 1898, discovery number 2. In the barium fraction this time.
And this was
Radium, from the Latin word radius for array. And it was in this paper, reporting on radium, that they first used the words radioactive and radioactivity.
They coined the terms. Wow. Okay, so they found evidence of 2 new elements.
Yeah.
But they needed proof, right? Solid proof.
Absolutely. To convince the scientific world, especially the skeptical chemists, Marie knew she had to isolate these elements in pure form, show their atomic weights, their properties.
And this turned into, well, the stuff of legends, didn't it? It really did. This isolation effort was heroic. They moved their lab, if you can call it that, to this miserable old shed.
I've read descriptions. Poorly equipped, drafty, leaky roof.
Unheated, awful conditions. And there, Marie set about processing literally tons of pitch blende residue.
Tons. Where do they get that much?
It was waste material from a mine in Austria, processing uranium salts. The Austrian government actually donated it to them. Lucky break, in a way.
Still tons of ore. How much radium did she get?
After 3 years of relentless work, performing what she called several thousands of crystallizations, just 1/10 of a gram of pure radium chloride.
1/10 of a gram from tons of rock. And the physical labor. She described stirring boiling vats with an iron rod almost as big as her.
Yes, being breaking with fatigue. It's almost unimaginable. Modern chemists work in fume hoods with safety gear. She was doing heavy industrial chemistry in a shed.
And polonium.
Proved impossible for her to isolate then. Its half-life is much shorter, only 138 days, so it decayed too quickly during the long separation process.
Despite the hardship, there must have been moments of excitement.
Oh, absolutely. She wrote about the joy of going into the dark workroom at night.
And seeing the tubes glow.
Seeing the feebly luminous silhouettes of the bottles containing their radium products. She called it a lovely sight, and one always new to us. Radium glowed, it produced heat constantly.
About 118 calories per gram per hour, the sources say.
Yes, and its rays passed through matter, ionized air. It was clearly something extraordinary.
And then there's the decision about patenting. They chose not to.
That's right. They deliberately refused to patent their isolation process.
Why? That seems counterintuitive. They could have been wealthy.
Their belief was that scientific knowledge should be open. It should benefit everyone. Pure research ideals.
But that decision had consequences, right?
It did. It allowed the radium industry to boom almost immediately. Companies jumped in, using their process, making money from medical applications and other uses, while the Curies struggled financially for years.
A noble decision, but with a practical cost.
Definitely. And her Ph.D. thesis in 1903, wrapping all this up, it was basically the death blow for the old idea of the indivisible atom.
Because elements could change, emit energy from within.
Exactly. Elements emitting rays, alpha, beta, gamma, later found to come from the nucleus, and even transmuting into other elements. It raised huge questions about conservation of energy.
Which tied into Einstein's developing ideas.
Immensely so. EMC squared gained a lot more traction because radioactivity showed mass converting to energy. It really kicked off the nuclear era.
The impact sounds enormous. New elements discovered, quantum mechanics, nuclear science.
Particle physics, astrophysics, geophysics. The foundations were being laid thanks in large part to her work. Over 30 new radioactive elements were found within a decade.
It's just staggering, and this led to their first Nobel Prize.
Yes, 1903. Physics. Shared with Pierre and Henri Becquerel.
And Pierre insisted Marie be included.
He absolutely did. The initial nomination was just for Becquerel and Pierre. Pierre wrote to the committee saying Marie's contribution was essential and she had to be recognized.
That speaks volumes about their partnership. But this work took a toll on them physically.
A terrible toll, though they didn't fully grasp the danger then. Pierre's hands were burned, scarred by handling radium tubes. Marie's fingers were cracked and damaged. Both suffered chronic fatigue, illness, likely radiation sickness.
And their notebooks are still radioactive today.
Highly radioactive, kept in lead-lined boxes. You need protective gear just to consult them. A stark reminder of the risks they took.
Then came unimaginable tragedy.
Yes. April 1906. Pierre was killed instantly in a street accident, run over by a horse-drawn carriage.
Just devastating. How did Marie cope?
With incredible strength, despite the overwhelming grief. The university offered her a widow's pension. She refused it.
Refused it. Why?
She famously said, "I am 38 and able to support myself." And she did.
By taking over his job.
They offered her Pierre's professorship at the Sorbonne. She accepted, becoming the first woman ever to hold such a position in France.
Another barrier broken, and her goal was to build a lab worthy of him.
Yes, a world-class laboratory. A tribute to Pierre and a continuation of their shared dream.
And she continued her own research, leading to
A second Nobel Prize, this time in 1911, and this one in chemistry.
for
For the discovery of polonium and radium, for isolating radium in pure metallic form. She achieved that with André de Berne and her overall study of this amazing element.
making her the first person ever, man or woman, to win 2 Nobel Prizes, and in 2 different scientific fields.
An absolutely unprecedented achievement, still incredibly rare today.
But this period wasn't all triumph, was it? There was intense public scrutiny.
Sadly, yes. Around the time of her second Nobel, she faced real hostility. She was nominated for membership in the French Academy of Sciences and rejected.
Why? On what grounds?
A nasty mix of things. Anti-Semitism, even though she wasn't Jewish, her maiden name sounded foreign. Prejudice against women in science, pure and simple. And xenophobia, she was still seen as an outsider, a Pole.
And then things got even uglier.
Yes. A slanderous press campaign erupted about her private life, specifically an alleged affair with a married colleague, Paul Langevin, who was also a physicist. It got vicious. There were calls for her to leave France.
How did this affect the Nobel Prize?
There was actually pressure from some within the Nobel Committee for her to decline the prize to avoid scandal staining the award.
Did she consider it?
No, she stood her ground. Famously asserted that her scientific work should be judged on its own merit, and slander about her private life had no bearing on its value. Incredible fortitude.
She just kept pushing forward. Then came World War I.
And she threw herself into the war effort, completely dedicated herself.
This is the story of the little Curies.
Exactly. She became the director of the Red Cross Radiology Service. Realizing X-rays could help locate shrapnel in wounded soldiers, she equipped mobile X-ray units.
Using cars.
Yes, about 20 vehicles, equipped with X-ray machines powered by dynamos run off the car engines. She drove them herself to the battlefields. These became known as petites curies, little curies.
Bringing radiology right to the front lines for the first time.
A massive innovation in military medicine. She didn't just equip and drive them, she trained operators too.
Including her daughter Irene.
Yes, Irene worked alongside her. Both were exposed to significant radiation doses doing this work. Marie even offered to have her gold Nobel medals melted down to help fund the war effort.
They wouldn't let her, thankfully.
No, the Bank of France declined. But her commitment was absolute. She felt she owed it to her adopted country.
After the war, she focused back on her Radium Institute.
Yes, the institute in Paris, which had actually been completed just before the war started in 1914, became this internationally renowned research hub.
Producing more Nobel winners?
Indeed. Including her daughter Irene and son-in-law Frederick Joliot-Curie, who won the chemistry prize later for discovering artificial radioactivity.
The legacy continued. And she helped establish one in Warsaw, too.
Yes, she helped found the Radium Institute in Warsaw in 1925. She also traveled, fundraising especially to the U.S. President Harding presented her with a gram of radium in 1921.
A gram of radium? That must have been incredibly valuable.
Hugely valuable, both scientifically and financially. She also served on international committees, like the League of Nations Commission for Intellectual Cooperation, always working.
But the years of radiation exposure eventually caught up with her.
Tragically, yes. Marie Curie died on July 4, 1934. The cause was aplastic anemia, a bone marrow disease almost certainly caused by her long-term exposure to radiation.
A sacrifice for science, and she received a unique honor after her death.
A very significant one. In 1995, her ashes, along with Pierre's, were moved to the Pantheon in Paris. She was the first woman entombed there based on her own merits.
Recognized for her scientific genius, her background, breaking barriers.
Exactly, a testament to her immense stature.
So let's talk about that long-term impact. We know she created the field of radioactivity. How did that reshape fundamental science?
Well, beyond just showing atoms weren't indivisible, the fact that elements could transform really hammered home the connection between mass and energy, bolstering Einstein's EMCY. It opened the door to understanding nuclear processes.
And laid the groundwork for, well, much of modern physics.
Absolutely. Quantum mechanics, nuclear science, particle physics all have roots tracing back to her work. Even modern astrophysics understanding stars and geophysics, like dating rocks.
And the practical applications today are just everywhere, aren't they?
Everywhere. Industry, agriculture, archaeology uses carbon dating, which relies on radioactivity, geology.
Energy sources, obviously. Nuclear power. Space exploration uses radioisotope thermoelectric generators.
And medicine. Diagnostics like PET scans use radioactive tracers. And of course, cancer treatment radiotherapy. Indispensable tools.
But that early enthusiasm for radium, it had a dark side. The radium girls.
A truly tragic story and a crucial lesson. In the early 1900s, factories hired young women to paint watch dials and instrument panels with luminous radium paint.
And they were told to lick the brushes to get a fine point.
Yes, they were ingesting radium constantly, and because radium is chemically similar to calcium,
It went straight to their bones.
exactly, it accumulated in their bones, leading to horrific bone cancers, particularly in the jaw, skull necrosis, anemia, other malignancies, just devastating.
But their suffering wasn't entirely in vain.
Their plight and the lawsuits they bravely fought provided some of the first solid human data on the dangers of internal radiation exposure, on radiation carcinogenesis. It led to major reforms in worker safety and understanding radiation hazards. Many of their remains are still radioactive, studied even today.
A terrible price for that knowledge. And there's no real way to get radium out once it's in the bone.
No specific decorporation therapy exists, though giving calcium might interfere a bit with initial absorption if given quickly. But once it's incorporated, it's essentially there.
Now, you mentioned earlier, there are places today that still use radium or radon for therapy. That sounds counterintuitive.
It does, especially given the Radium Girls story.
Yeah.
But yes, places like Jakimov and the Czech Republic, where the Curies got their pitch blend, and Bad Gastein in Austria have spas offering radon therapy.
How does that work?
People bathe in radium-rich spring water or inhale air with high concentrations of radon gas, which is a decay product of radium. It's used primarily for inflammatory joint diseases, like rheumatoid arthritis.
Is there evidence it works? Is it safe?
It's controversial. The radon levels are way above what's considered safe for homes. Proponents suggest low-dose radiation might have anti-inflammatory or immune-modulating effects, the hormesis idea, maybe. But the mechanism isn't fully clear, and regulatory bodies in places like the U.S. are very skeptical. It really raises questions about dose response.
Fascinatingly, though, radium itself is making a comeback in a very targeted way in medicine.
Yes, this is really exciting. A specific isotope, radium-223, marketed as Xofigo, is used in targeted alpha therapy.
Alpha therapy, how's that different?
Radium-223 emits alpha particles. These are heavy particles, like tiny cannonballs, but they travel only a very short distance, just a few cell widths.
So they deliver a powerful punch but don't damage distant tissue.
Exactly. Because radium acts like calcium, it naturally targets bone. So for cancers that have spread to the bone, like some prostate cancers, radium-223 goes right to the tumors in the bone and delivers a highly cytotoxic dose with less damage to surrounding healthy marrow compared to other radiation types.
A direct descendant of Marie's discovery, used with much greater understanding of the risks and benefits.
Precisely. It's a testament to how foundational her work was.
And beyond the science itself, her legacy as a role model
Is immense. She remains a global feminist icon. She didn't just do groundbreaking science. She did it while smashing through gender barriers in a deeply patriarchal society.
proving what women were capable of.
Absolutely. She paved the way. Think of the women who followed, inspired directly or indirectly. Her own daughter Irene, also a Nobel laureate, Dorothy Hodgkin, Nobel in chemistry, pioneer of X-ray crystallography, Rosalind Franklin, whose X-ray crystallography was key to the DNA structure, Gertie Corey, Nobel in medicine, who used radioactive isotopes in her metabolic research.
That incredible lineage.
It truly is. And there's that lovely quote from one of the sources, suggesting the Curie's biggest discovery might have been finding each other.
Highlighting their partnership. Pierre himself apparently mused about the double-edged sword of scientific discovery, like Nobel's dynamite capable of great good or great harm.
Yes, but he remained optimistic, believing humanity would ultimately derive more good than harm, a hope we still grapple with today.
What an incredible journey, really, through Marie Curie's life and impact, her relentless curiosity, those painstaking methods.
And the profound insights. discovering new elements, radioactivity itself, fundamentally changing how we see the atom, the universe.
And doing it all against such odds. Personal tragedy, scientific skepticism, public hostility, laying groundwork for whole fields of science and medicine.
All while being a trailblazer for women in STEM. Her resilience is just awe-inspiring.
It really is. And her story, especially thinking about the radium girls, the personal costs, the barriers she faced, it leaves you with a pretty powerful thought, doesn't it?
Definitely.
Yeah.
It makes you wonder, how many other potential Marie Curies has the world missed out on? How many groundbreaking discoveries never happened because brilliant minds, especially women or people from underrepresented groups, just hit too many walls?
Faced too much prejudice, couldn't get into the lab, weren't taken seriously.
It's a sobering thought. It reminds us that creating an inclusive space for anyone with curiosity isn't just about fairness, right?
No, it's about unlocking our full human potential for everyone's benefit.